So what is space phasor and what is alpha beta reference frame? What is DQ reference frame? These concepts are very important in control of induction motor or grid connected PV system or PMSM motor control, etc. Or to give pulses for a grid-tied inverter. So what is space phasor? A space phasor is a single rotating vector that represents the combined effect of multiple sinusoidal quantities. Let us suppose we have three sinusoidal quantities like VA, VB, VC. We can represent all the three quantities into a single vector like what we are discussing in rotating magnetic field of a three-phase induction motor. Let us see here. So these are the three sinusoidally varying waveforms, but these are considered like if you consider the instantaneous value of voltages at any instant, let us suppose at 30 degrees or 60 degrees and so on and so forth, we have the phasors like this and its instantaneous magnitudes are represented here. If you add these things vectorially, we will get a resultant vector something like this. At a 30 degree, we get a resultant vector is at 0 degree. At 60 degree, at 0 degree, we get resultant vector of 0 degree. At 30 degree, resultant vector is 30 degree. At 60 degree, it is like this. Means if you observe the pattern, the vector is rotating in anti-clockwise direction like this from here to here. That is from 0 to 330 degrees. Then the 360 degrees same as 0 degree means it is rotating in the anti-clockwise direction. Means all the three sinusoidally varying voltage waveforms are converted into a single resultant vector, that is a rotating phasor. We can say this is a rotating phasor. This is something like a space phasor. Now here if you observe A equal to e power j 120 degree, A square is e power j 240 degree, where this A is a vector operator, phase shift operator like I in complex number. Let us express I y. In that I represents 90 degree phase shift. In the same way, here A represent 120 degree phase shift. So we are representing this as V bar is equal to 2 by 3 times of VA plus AVB plus A square VC. So why we have to multiply the 2 by 3? We'll discuss later on. So using Euler identity, we can represent the cos theta as e power j theta plus e power minus j theta by 2. Substituting the values in that equation, we can reduce down like this. That is Vm by 2 e power j theta plus e power minus j theta by 2 plus a times of e power j theta minus 120 plus a square times of e power j theta minus 240 and so on. If you observe here, e power j theta and e power minus j theta, these two represents one is a positive and the other is a negative rotating components. So we can separate it into positive and negative. If you consider only positive components, this is e power j theta plus a e power j theta minus 120 theta plus theta minus 240. But a is e power j 120 degree. That is, you can write it in the phasor form, or if it is in magnitude phase form, 1 at an angle 120, or in phasor form you can write it as e power j 120 degree. E power a, if you bring this one to this side, you will get it as 1. So you can substitute a e power minus j 120 as 1. So a square e power minus j 120 minus j 240 as also 1. After substituting all this, we will get a 3 by 2 Vm, that is 1.5 Vm e power j theta. Means it is j e power j theta represents, it is a space phasor rotating at a speed of theta into that is omega t with a magnitude of 1.5 Vm. If you consider the negative sequence values are reduced down to this, and we know that 1 plus a plus a square is equal to 0. So completely the negative sequence components are 0. When the phase sequence is, when the phase system is balanced, then we don't get this negative phase sequence. So it is absolutely positive. So hence, VA plus AVB plus A square VC can be reduced to 3 by 2 Vm equals J theta. It's a single rotating phasor, we can represent it as a V. The amplitude of the AC signal can be manipulated by multiplying the phasor with an appropriate scalar. Here, to make it clear, we multiply it with 2 by 3. That is, we are normalizing the above quantity in order to remove this 3 by 2 factor. So, we are multiplying this one VA plus AB plus A square VC with 2 by 3 in order to remove this 3 by 2, so that we will end up with the equation Vm e power j theta. See, this is VA VBBC frame and this is space phasor frame. We are converting alternating quantities VA VBBC into a single vector space phasor V bar. So V bar equal to 2 by 3, VA equal J0, VB equal J 2 by 3, VC equal J 4 by 3. And if you do the reverse action, we can convert this V bar to back to VA VBBC like this. And we can represent VA VBBC as real part of V e power J0, real part of V e power minus J2 by 3, V e power minus J 4 by 2. So the main thing here we need to observe is VA means Vm cos omega t, VB means Vm cos omega t minus 120. But here again we are multiplying it with e power J2 by 3. Why we are doing this phase shift to 2 times phase? The one is the time phase and the other one is space phase. In time phase, we consider omega t minus 120 in sinusoidal form, whereas this e power j2 by 3 is belongs to space phase. That is used in the space phasor transformation. To make it clear, just look at it. VA, VB, VC are the instantaneous values. Assume its values are 5 minus 3 minus 2 minus 3 at one instant. These are just scalar values. They have no direction. To obtain the resultant magnetic field, each scalar must be placed along with its axis of its winding. Therefore, phase A acts 0 degree, that is VA equals J0. Phase B acts 120 degree, VB equals minus plus J2 by 3. Phase C acts minus VC equals J4 by 3, that is 240 degree. Here, this represents a complex form. E power J0 means cos 0 plus J sin 0. E power J2 by 3 cos 2 by 3 plus J sin 2 by 3. As complex a number, it has a magnitude and a phase angle. So that phase angle provides the spatial rotation for us. If you take the powers, P of t, that is, you can say it as a apparent power equal to VGIA, VGBIB and VGCIC. This is the total power, total active power. So we can write it as real part of V power minus J0, real part of I power minus J0 and real part of this and real part of the third quantity. We can write like this. By using the identity, real part of V into real part of I is written as real part of Vi plus real part of Va conjugate whole divided by 2. The expression for P of t becomes like this. 3 by 2 real part of Va conjugate plus 3 by 2 real part of Vi e power minus J2 by 2. So this will give us the information about the active power where P is 3 by 2 e power VI conjugate and Q is 3 by 2 imaginary part of this VI conjugate. Alpha beta frame representation of a space phasor. It is always easier to consider the variables as real valued functions of time rather than the complex phasors. So V bar is V alpha plus J beta, means so this is a different frame. So one is what we discussed earlier is phase phasor frame. This is just a DQ frame, means we are converting all the rotating or varying sinusoidal quantities into just a stationary frame of reference V alpha V beta. So that this can be represented as what we have earlier we discussed. This is the phase Phasor form before we have seen the two-third of VA, VB, VC like this. So in this we can write it as V alpha V beta equal to two-third of VA, VB, VC. We can write it in the matrix form like this. Means here if you expand e power j 2 pi by 3, it is cos 2 pi by 3 plus j sin 2 pi by 3. Cos 2 pi by 3 is minus 1 by 2 plus j sin 2 pi by 3 is that is for VC cos 4 pi by 3. This is cos 0. Cos 0 is 1, cos 2 pi by 3 is minus 1 by 2, cos 4 pi by 3 is minus 1 by 2. Like that, the imaginary components e power sin 0 is 0, sin 2 pi by 3 is root 3 by 2, sin 4 pi by 3 is minus root 3 by 2. Like that, we can get this matrix. So VAB, V alpha beta equal to 2/3 of C times of VAB, where this C represents the matrix what we have seen earlier. If you transpose that C, we get this one. That is, we are transposing the row columns. We can get it as C transpose to get back the VABC from V alpha beta. The apparent power in alpha beta system is considered as 3 by 2 VA, that is 3 by 2. V means V alpha plus J V beta, I is I alpha plus J I beta, then P plus JQ, that is S apparent power, can be written as 3 by 2 into, if you just do this product, I alpha plus J I beta conjugate means I alpha minus J I beta. If you do this product, we will get this one where 3 by 2 V alpha I alpha plus V beta I beta is active power, and 3 by 2 V beta I alpha minus V alpha I beta is V active power. The ABC to alpha beta, this transformation we call it as a Clarke's transformation, where we want to replace the 3 time varying phase quantities into 2 orthogonal stationary components. It simplifies the analysis of control of 3-phase system very easily. Let us look at this one. This is the 3-phase components VA, VB, VC, and we are transforming this 3-phase quantities into 2-phase stationary components, that is I alpha, I beta. Means we are transforming this IA as, we have to do component vectors of this IA, IB, IC onto I alpha and I beta, so that we can get this equation. I alpha can be written as 2/3. This constant is, anyway, we will discuss earlier, into IA, that is minus half IB minus half IC, and I beta can be written as 2/3 of root 3 by 2 times IB minus root 3 by 2 times IC. So how we get these values we have already discussed in that C matrix. So IA is Im cos omega t, IB is like this, IC is like this, and the instantaneous component, the instantaneous value of IA, IB, IC at any instant is 0 magnitudes. And space phasor alpha beta representation is IS bar equal to I alpha plus J I beta and I is at angle theta. You can represent like this. Its magnitude is root of I alpha I beta square, and theta is tan inverse of I beta by I alpha. So representing the resultant rotation magnetic field produced by the 3 phases. So here also it is a single vector rotating at the same speed of the, so it is something like a, so this IS is the resultant of IA, IB, IC at one instant of time. This is alpha beta frame. This is not rotating, so we call it as a stationary frame of reference. It is not rotating. When rotation is not required, we use alpha beta transformation. The alpha beta frame is stationary. It is sufficient for applications such as SVPWM, space vector voltmeter modulation, to generate reference signals for the switches. We can use that rotating ABC phasors into stationary alpha beta components, and then we can generate the PWM signals to the all switches for the inverter. And the grid connected inverters, if you want to observe or analyze the grid voltages currents in a space vector or space vector visualization showing the rotating magnetic field or rotating vector, rotating voltage vector. And instantaneous PQ theory, active and reactive power calculations. So for this, we usually go with the alpha beta frame, but before that we have to first transform ABC to alpha beta, then sorry, for instantaneous power, for this active and reactive power calculations are often directly performed with alpha beta calculations. The general analysis simulation also we use this. DQ frame representation for space phasor. So this is the third one. The first one is space phasor representation. Second one is stationary reference frame alpha beta. This is the rotating reference frame DQ. The DQ reference frame rotates at exactly same angular speed as the rotating magnetic field or space vector. Space vector is only single vector, whereas DQ frame is a two perpendicular vectors. One is D and the other one is Q. These two vectors, that is this DQ frame, is rotating at the same speed of the space phasor. As a result, the rotating vector appears stationary with respect to DQ frame, making it easy to control the magnitude of the components. See, this is alpha beta 0 to DQ0 Parkes transformation. Here we have our alpha beta vector, and the resultant is Vs. The resultant is Vs like this. The angle between Vs and V alpha is theta. It is the instantaneous angle of the space vector. Here we have rotating frame of reference, that is D and Q, which are mutually perpendicular to each other like alpha beta, but alpha beta will not rotate, whereas the DQ will rotate at some angular speed. And if you consider here, it is rotating at theta. Actually Vs is rotating at some speed, and DQ is also aligned to rotate with the same speed, so that this DQ vector will represent this Vs accurately. So to know this analogy, simply assume we have a ceiling fan. We have to control the length of the each wing of the ceiling fan when it is rotating. If the fan is rotating, how to control the length of the each wing? The only way is we also need to rotate along with the wings of the fan, so that we are stationary with respect to fan. If the fan is rotating at 1500 rpm, we also rotating at 1500 rpm, then the fan wing is stationary with respect to us, so that we can adjust the length of the wing. So here the fan, assume it as a space phasor Vs. Now ourselves we can assume it as a DQ frame. So we have to align with the fan wings like that. Vs is rotating at one speed. The DQ frame is also required to align with Vs in such a way that if you control D or Q components, you can control A, B, C components. So that is the thing about how to control the varying values, that is VAB, BBC, sinusoidally varying quantities. by using this dq transformation. What is dq transformation? Here Vd, Vq, V0 is equal to, this is the transformation matrix, into V alpha, V beta, V0. Usually we are not considering V naught, so this is a zero sequence component, you can say. Usually we will do Vd, Vq to V alpha, V beta, or V alpha, V beta to VABC, and so on. This is V alpha, V beta, V0 to, how to convert Vd, Vq to again V alpha, V beta, back to this. So if you do inverse for this, you will get this matrix. See, this theta can be written as omega t plus theta naught. What is this theta naught? We will discuss. That we know our space phasor V of t equal to 2/3 of Va plus Vv is like this. That is Vm e power j phi. So this is represents the stationary, that is the space phasor e power j phi represents the space phasor, where omega is written as d phi by dt. If you multiply this, d phi equal to omega dt. If you want phi, just integrate this over time, where this is phi naught. Here phi is the angle of the space phasor with respect to stationary alpha axis. As we have seen in the earlier slide, the angle between that Vs and alpha axis is phi. So that is the space phasor angle. So we can represent this V bar in alpha beta frame as V alpha plus j V beta. So V alpha beta can be written in matrix form as 2/3 of C times of VABC. We know about this C, we have already seen in alpha beta transformation. Space phasor can converted into dq frame by introducing a phase shift to the phasor, that is another phase shift called e power minus j theta. So V dq equal to V bar into e power minus j theta, where V bar is V alpha plus j V beta, is the stationary frame of reference, and we are converting this to rotating frame of reference by multiplying it with a phasor quantity e power minus j theta. Then what is this theta? Theta equal to theta naught plus 0 to t omega 1 of tau theta. So the same thing we can use here also, whereas this phi is the angle, where this phi is the angle between the space phasor with respect to stationary axis, where this theta is the angle through which the dq frame is rotated from stationary axis. Both represents the angle of rotation, but one is space phasor and the other one is dq frame. This is single vector and this is like this. So this is something like a single vector like this, space phasor, that is Vs, whereas this represents the dq frame, which are mutually perpendicular vectors, which is Vd and the other one is Vq. So this is also rotating at the speed of omega, and this is also rotating at a speed of omega 1. This is rotating at the speed of omega, this is rotating considered at a speed of omega 1. Now we need to match this omega and omega 1 in such a way that if these two speeds are same, it is like we can control the Vs, means it is the combination of Va, Vb, Vc vectors. So you can control the Va, Vb, Vc vectors by controlling Vd, Vq. So that is the logic behind this mathematical model, where theta is the instantaneous electrical angle, theta naught is the initial electrical angle. What is this theta naught initial electrical angle that we have discussed in the before slide? This is the initial angle of the rotating d axis measured from the stationary alpha at time t equal to 0. Assume at time t equal to 0, the angle is 30 degree from alpha axis, then theta naught equal to 30 degree. So you have to add this 30 degree with integral of omega 1 tau d tau to get the overall angle. The theta is the instantaneous electrical angle, the rotation of d axis or space vector. Omega 1 tau is the angular velocity which may be vary with respect to time, and tau is the integral variable. In stationary frame it is mentioned theta angle means it is at any arbitrary time t. If the stationary frame is mentioned at t equals 0, then it is theta naught. Vd plus jVq, this can be written as 2/3 of Vm e power j theta. Theta means theta naught minus phi naught minus theta naught into e power j integral 0 to t omega minus omega 1 t. So we can represent this one like this. Means 2 by 3 Vm e power j phi into e power j theta. You can write it as 2 by 3 e power j phi into j theta. Why? Because Vd Vq, actually V alpha V beta means V alpha plus j V beta equal to 2 by 3 Vm e power minus e power j phi. This is 2 by 3 e power j phi. But here Vd Vq is V alpha beta into e power j theta. So we can write it as 2 by 3 Vm e power j theta into e power j phi conjugate. Means we can write it as 2 by 3 Vm e power j into theta minus theta naught phi naught minus theta naught plus e power j 0 to t omega minus omega 1 t. If you make omega equal to omega 1, if you adjust using your control strategy or PLL, you adjust these phasors are same, then we can achieve this part as 1. So this become a simple quantity which is not varying with respect to time. Means this Vd plus jVq you can control very easily, as this is independent of time, which makes the Cartesian quantity dq being a stationary coordinate. This is feasible by synchronizing the angular frequency dq with the original space vector in the synchronous frame. Here we need to understand that theta and phi need not to be equal, where this phi is stationary phase angle, that is angle between alpha axis and space phasor axis Bs, and this theta is the angle between the d axis of the dq frame and alpha. So these two need not be equal at any instant of time, but the rate at which this theta, that is dq frame, is rotating and the rate at which the space phasor is rotating must be equal. Then only these two are synchronously changing, so that we can, one is stationary with respect to another, so we can easily control the dq frame, so that we can control ABC alternating quantities VA, VB, VC. So V dq is equal to V bar e power minus j phi, we know this, and V bar is equal to V alpha plus j V beta. After substituting this, V alpha plus j beta into e power j theta can be written as cos theta plus j sin theta. Why we are doing this is in order to represent VD VQ in terms of V alpha V beta, so that we can get this matrix and assume this is R. So VD VQ can be written as R times of V alpha beta. So this matrix is the conversion matrix to convert DQ frame alpha beta frame to DQ frame. If you want to do the reverse one, that is a V D, again we need to obtain alpha beta from DQ. We have to multiply VDQ with R inverse. Hence VDVQ equal to this one. Usually this is the phase phasor. So VDVQ can be obtained as 2/3 of this matrix, and this transformation is called Fox transformation. Here what we are doing is we are converting V alpha V beta into VABC by using the matrix C what we have discussed earlier. So if you are multiplying the matrix R with C, then you will get this Fox transform vector T, that is cos theta minus 2 pi by 3, cos theta minus 4 pi by 3, minus sin theta minus 4 pi by 3, minus sin theta minus 4 pi by 3 into VABC. So we can consider this matrix as a capital T. Now we have seen three matrices. One is C. This is to convert ABC frame to space phasor frame, and the matrix R, which is used to convert alpha beta frame to DQ frame, and this is the phasor. This is the matrix T, which is used to convert ABC frame directly to DQ frame. Now the apparent power using this DQ transformation technique is 3 by 2 VI conjugate, whereas is equal to 3 by 2 VD plus JVQ into ID plus JIQ whole conjugate. V plus JQ is, we can write like this, VDID plus VQIQ plus J times of 3 by 2 into VQID minus VDIQ. So this represents the active power and this represents the reactive power. Where we use this DQ transformation. So when rotation is required, we use this DQ transformation. Use DQ transformation when you need to control the quantities such as rotating with the machine, such as rotor flux, stator flux, torque producing current, PMSM or induction motor, currents, field oriented control. The DQ transformation rotates the reference frames so that these quantities become nearly constant DC. One important case is in case 1 only generating PWM signals alpha beta is enough. Suppose you have a 3-phase inverter connected to grid. If your goal is to simply to generate switching signals using space vector SVPWM, the inverter switching vectors are defined in stationary alpha beta plane, so that there is no need to rotate the reference frame. In case 2, controlling a grid current or power using decoupling. Earlier we have mentioned controlling this using controlling this using alpha beta. Actually, if you want to convert ABC to DQ, we can first use ABC to alpha beta and then alpha beta to DQ. So, or we can suppose we want to control active power, reactive power feeding to grid, then we can go with DQ control. In grid current we can control, and DC link voltage also we can control using this DQ reference theory. Means we are transforming the live VA, VB, VC vectors or IA, IB, IC vectors into DQ reference vectors, so that we can see that becomes rotating phasors, DQ rotating frame. Means we can control the D and Q individually to a desired value. Then DQ transformation is almost always used. Thank you.